Hey there folks, and welcome to our second video lesson on applications of multiple integrals. Today we're going to see how to use double integrals to find the total amount of a given quantity. Now I know that sounds vague, but it's supposed to be vague because this discussion can apply to many different types of scenarios. Up to now we've seen several applications of multiple integrals, including finding areas, volumes, or average values. But it turns out there's a whole host of other applications that we get by viewing our function fxy as some density function. So throughout this lesson, we're going to assume that fxy represents the density of some quantity at a point xy over some region R. If that's the case, then we can interpret this double integral of f of xy over the region R as the total amount of that quantity found throughout our region. To see why this makes sense, let's pretend that we have a flat object that occupies this region R in the xy plane, and we'll assume for the time being that that object has a constant density throughout this region. If that's the case, then its density, rho, is equal to its mass divided by the total area it occupies. Rho equals m over a. If we rearrange this, we get that the object's total mass is the density rho times the area A. But what if our object doesn't have constant density? What if the density changes as we move throughout our region? Well, if that's the case, maybe then the density can be represented by this curved surface living above our region. At the point xy, the density is given by the height of the curve f of xy. If we still wish to know the total mass of our object given its density, well, now we can't use this formula, mass equals density times area, because the density isn't constant. But what we can do is chop up our object into a bunch of tiny little pieces, and on each one of those pieces we can say, okay, the density will be approximately constant. So we can use this formula to approximate our mass on each one of those pieces. On this piece, for instance, our object's mass is approximately the area of the base times the height of our density function. What we're saying here is that the object's mass is approximately the volume of this box. If we do this same thing on each of our pieces and add up those approximations, we're going to get an approximation for the total volume of our object over the region R. And by taking finer and finer cuts in the x and y axis, we're going to get a better and better approximation. Now, does this feel at all familiar? Hopefully it does, because this process of cutting up our region and adding up these volumes is exactly what we went through when we defined our double integral. So maybe it makes sense. If f of x represents a density, then the double integral of f over the region R represents the total amount of our quantity that occurs throughout the region. Here are just a few situations where we can use the ideas from the last slide to find the total amount of a quantity given its density function. So for example, suppose that your function fxy represents the density of mass of some object over a flat surface. In that case, the double integral of f over that region R is going to represent total mass. You can see here that the units will match up. If f of xy represents density, then maybe it's measured in kilograms per meters squared. dA represents a small change in area and is also measured in units of meters squared. Now check it out. The meters squareds are going to cancel out, and you're left with just kilograms. The integral is sort of like a sum, right? We're summing over that entire region, so we're adding up the kilograms, we get the total mass. The same is true if we consider f of x to be a population density. Maybe it describes the distribution of people living throughout a city. In that case, the double integral of f of xy will represent the total population. Again, the units match up. F of xy is the density, so it measures people per square kilometer, let's say. dA is the change in area and is also measured in square kilometers, and once again we get a cancellation. So this integral is sort of like the sum of all people. It gives us a total population. For our third and final example, suppose that f of xy represents the density of charge over some surface R. In that case, the double integral over R of f of xy represents the total charge across that region. No surprises here, we see the same behavior in our units as we saw above. So if our charge density is measured in coulombs per meter squared, and our area is measured in meters squared, then once again we have a little cancellation, and we're left with a sum of coulombs. That gives us the total charge. Okay, here's a concrete example to illustrate our new concept. Suppose that electric charge is distributed throughout this unit disk, x squared plus y squared is less than or equal to 1, so that the charge density at point xy is given by this function. Sigma xy equals the square root of x squared plus y squared measured in coulombs per meters squared. We want to know the total charge over our region. Okay, now we've just learned that the total charge is equal to the double integral of our charge density function. So let's write this down. The total charge is equal to the double integral over our region, x squared plus y squared is less than or equal to 1, of our charge density function root x squared plus y squared dA. Now at this point, I bet you're getting pretty good at spotting integrals that could be best handled in terms of polar coordinates. And this is one of them. Here you can see that we're integrating over the inside of the unit circle, which is something that works very well in polar coordinates. I also see that we're integrating the function root rho squared, which is another indication that converting to polar coordinates is probably a good choice. So let's go ahead and switch to rhos and phi's. Since we're integrating over the entire inside of the unit circle, phi is going to go from 0 to 2 pi, rho is going to go from 0 to 1. We're integrating the function root rho squared, which is just rho, and now I multiply by my new area factor, rho d phi. At this point, we can split up our integral into a product of a phi integral and a rho integral. I have the integral from 0 to 2 pi d phi times the integral from 0 to 1 of rho squared d rho. It's not too hard to see that this first integral will evaluate to 2 pi, and for our second integral, an antiderivative with respect to rho is rho cubed over 3. We evaluate from 0 to 1. This gives us a total charge of 2 pi over 3 coulombs.